Hi everyone, and welcome to the final review for EECE 2310 Visual Systems. We'll start here in 2 to 3 minutes. We still got about that much time till 7 o'clock. If you guys can let me know if you can hear me. Yep, I already see one message. So does anyone know when you guys' exam date is? Tomorrow. Okay. Let me try to turn up the audio for you guys. Let me know if that audio sounds a little bit better now. All right, awesome. Louder audio now, and I'll try to talk a little bit louder. Before we get started, is there any topics in general that anyone would like to be reviewed tonight in particular? Okay, SOP, POS conversion. I'm going to do shared terms. Um, I can try to do, I think I have one example from a past homework and whatnot that I can maybe work through. And it seems like a lot of computer architecture I can also go over. Register files and adders, if you could be a little bit more specific on what you want reviewed, I can help you guys with that. So I'm going to go ahead and start the stuff tonight, and we're going to go over some computer architecture problems. So you guys in this class primarily work with the MIPS processor. It's one of the simpler computer architectures out there, and you guys work with the single cycle machine. So this is kind of a diagram of the single cycle machine. And what a single cycle machine means is that you only all these control pieces right here, they're going to execute in one clock cycle. It doesn't take multiple clock cycles to execute. Let me know, do you guys do a pipeline processor in this class? If you guys don't do pipeline processors, then we can stick to this single cycle example. But so you need to know how to convert these instructions to machine code, and then kind of see how the data flow in this processor is going to be. Okay, no pipelines, I won't go over those. All right, so let's go ahead and start working on this particular problem here. We have add immediate instruction. And this, remember in at least the MIPS machine, there are 3 types of instructions. So we have 3 instructions, right? We have what I would call R type, that's register. We have let's say the I type instructions, right? These are immediate type instructions. So this is going to be like your math, right? So that's like add, sub, stuff of that nature. This immediate is like the load immediates we have, or actually more like the load word and the store words. Those use immediate values. Add I, sub I, these types of deal. And our last type of instruction we have are like these jump type instructions, right? So that's jump. It's primarily used for jumps, yeah. Yeah, so we want to convert this instruction to machine code. So we first need to know, what type of instruction this is. So this is add immediates, right? So we're going to be looking at this guy right here. This immediate one. And what type of format does the immediate instruction take? We need to figure that out. So if we have an immediate instruction, right, we're going to have some opcode right here, or some operation that's going to be, add I, sub I, something like that. And then you're going to have what follows behind that, right? So it's generally in the format of RT. So this is the RT register. Usually have an immediate value and then an RS register. So that's the general format of how that works. And that's how it's going to work if you've got like a load word and a store word. If you have like these arithmetic ones, generally is written as the op. Then you have the RS, RT, then an immediate value. All right, so let's start breaking this down. So what we want to focus first, so let me erase some of this stuff here. So first, right, we're going to be working with this immediate value, and we know we have some information that will kind of help us with this problem. So right here we have kind of the different mnemonics we have, and what opcode they're going to have, right? So we're right now looking at the immediate type of instruction, this one right here. Because we're wanting to do immediate instructions. So let's look at what this opcode needs to be. This opcode is typically 6 bits, right? And it is 08, right? So that's our opcode. So we're going to start with, it's going to be hex 08 right here, right? And then we want our RS, our RT, and then we're going to want that immediate value there. So right, I said this instruction we're working with, let me write it down right here. Let me switch guys can see that. So our instruction we have is $T3, $T2, and 10. Yes, and we can go over the different types of kind of polls and interrupts. Right, so I have this, and I know from this right here, this format right here, that this is going to be our RS register. This is going to be our $RT register, and this is the immediate value we have, right? Right, and this entire instruction is 32 bits, right? So this is like bit 31 all the way over here, and this is bit 0. Each of these registers, these take up 5 bits, right? Because MIPS has 32 registers, so 2 to the power of 5 is 32. 6 bits for the opcode, and we have 12 for the immediate. I think I'm missing some actually. Look at my notes right here, so I give you guys the correct format. Immediate 16 bits. That's why I was off. Right. Okay. So you said we learned $T2 as the RS and $T. That's interesting. It might be the other way around then. $T2 should be for RS. Right, okay. I may have had these backwards. Thank you, guys. So this should be RS, this should be RT, right? So you'd flip these around. RT here and RS. Does that look right? Okay. All right, so we need to occupy these bit fields here. So, right, if we go back to our diagram here that you guys will probably be given on the test. You can see that, so, right, this is the RS right here, and this is RT. And so we said the RT in this case is that RT in this case is $T3, and so $T3 is address 11. So right, we put 11 there. $T2 is address 10. Put 10 there, and then our immediate value is 10 in this case. Right, and I'm writing these down in decimal. So let's go ahead and convert this to binary. So we have 6 bits for this hex 08. So let's go ahead and convert this over. So And then we have 11 in binary. Let me switch over here. Then 11 in binary is going to be, and so, right, you only need 4 bits to represent 8, but we're going to pad it up to 6 bits. So here, to write 11, it's just 1, 0, 1, 1, but I'm going to add this 0 right here to pad it up to 5 bits. Right here for this 10, to write 10, right, it's just 10 is 1, 0, 1, 0, but I'm going to pad it and add a 0 right there. And then the 10, right, we can write 10 as 1, 0, 1, 0, and then, right, this would be, we would have 14 zeros here. So does that all look correct? So this is how we would decode this particular instruction, how to convert it to machine code. And in the previous review, which should be on YouTube, I decoded another instruction. So if you guys want a little bit more examples, you can look on that one. So someone's asking for load word would, yeah, that's 12 zeros, right? 16 bits. My mistake. So someone's saying this is not correct. RS is 10, RT is 11. So let's look back here. So right, we have, let's just rewrite this instruction here, add I. And then we have $T3, $T2, 10, right? And we said how this should be, this should be right. So is this looking correct, guys? I'm right now trying to look at the chat and you guys at the same time, right? Right, so we have this. So this one right here is $RT, and this one right here is $RS. And so we went back to this slide after we did that. And we said, well, this $RT is $T3, which was 11. And this $RS right here is 10. And then we went back to this slide right here, or let's go back to this. We said we want our opcode as $RS, $RT, and the immediate. So yes, I may have had this backwards here. Right, exactly. I think I switched them over. Right, so let's flip these back over. All right, so is this looking correct now? Right, all right. Sorry about that, guys. Got a little mixed up there. All right, so, right. I'll maybe just do another one of these examples just for sanity's sake, but let's go back to the actual diagram here and see what the instruction flow is going to look like in this particular diagram. So I might just go here so I can actually edit this image right. So what actually goes on during the execution of this instruction here? So, right, so this is the program counter right here. So we can increase the size of this. We have the program counter right here. And what this does is it holds the current instruction address, right? So when we start execution, this add I immediate instruction is at some point in memory, and that's which is held here. This is the instruction memory. So what happens now is we begin, we load the instruction, right? And then the individual bits of the machine code that we get decoded will go out here. So, right, RD. In this case, we don't have an RD register. We have RS and RT. So, right, we said that RS in this case was $T2, right? And this is going to be $T3 right here. So those are going to point towards those. So in our data out, right, we should get those out. So, right, we have this immediate instruction here that I was talking about. We have this 10, right? So this has bits of 15 through 0 here. So this 10 is going to appear right here, right? Because it's going to get decoded, right? We encoded the immediate value and the last 16 bits of our instruction. So this 10 is right here, and it's sign extended. The reason why we're doing the sign extension right here, why the sign extension exists, right, is we want to add 10 to whatever the value and $T2 is, right? And what's going to happen there is, you know, we have a 32-bit value in $T2, and this, right, we use 16 bits to encode it. So we want to extend, we want to make this 16-bit number a 32-bit number, because our ALU takes 32-bit numbers. So this sign extension just makes it from a 16-bit immediate value to 32. It's just extending the sign, right? So we use a different color. So right here, we have this immediate value. That's going to go through here. It's going to go through here, right? And it's going to arrive at this mux. Well, with the ALU, I want to add the immediate value to $2. So this mux is going to select this line right here. So that's how that data flow is going to work. We're going to go back here, right? So let me get another color. So right here, right, this, we said that $T2, right, is, we have $T3 right here, and that's where we want to store the result. So that's going to go here, right? And since we want to write back the value of whatever this operation is back into $T3, right here, this mux is going to select this path, right? Because we want to put $T3 as the RD, because that's the destination, because we want to write back data to $T3. So that's going to do here. It's also going to go into here, but you see, you know, RT is going to come out right here, but we're not selecting it in the mux, right? It's going to stop right here. It's not actually going into the ALU. So whatever comes out here in data 2 is irrelevant. And right here, this is where the value of $T3 is going to come out, or $T2, I should say, right? Right, we have $T2 is going to come out right here. Right, and so we have the ALU. So if you need to write data into the register block, you need to set the RF write address. Yeah, so RF write enable is going to go high, right? Because we're going to do a data write back to $T3. Right, so if this is enable high, right, this should be like a 1 here. So right here, we're going to have a 1. Because you're going to see here, right, we're going to have some kind of LU calculation right here. And what's going to happen is this ALU is, so right here we have the result, and we want to write this back to $T3. Like the one at the top. Yeah, so this control line right here. Right, you want to set to 0 because you want to select the this first mux output, right? You don't want to select this one. So yeah, this one you're going to set to 0 because you want to select the first one. Yeah, I understand your question now. All right, this one's going to be set to 0. All right, so what's going to happen here? Our ALU result is going to come out right here, right? And we want to write this back to the register block. So we're not writing to main memory, right? So we don't need to do anything with this data memory, right? So these control lines are both going to be zeros, right? We're not really doing anything. We're not reading or writing from main memory. And so this, the result of our calculation is going to go down right here, right? And see what this line does right here. It goes back over here, and it's our write data. Well, we want to write data to $T3, which is getting sent via right here, since we set this RF write address to 0, right? So for this mux, we want to take this path, right? So it goes through like this. So that means this control line, we want to make 1. This control line is going to be a 1, right? Because we want to select this bottom part of the mux, not the top, because we want the data going into the register block to be direct from the ALU. So does that instruction make more sense? I know we had a little fumblings with the getting the register file or decoding the machine instruction, but hopefully this flow is a little bit more easy to understand. Bottom 0. Right, okay. It just depends on the said right addresses. Yeah, I have a different convention, I guess, right? So if you make, are you saying the bottom is 0? Okay. So if you make the bottom of the mux 0, like this is 0 and this is 1, then these will be flip-flopped, right? So maybe I should do it how Dr. Kogan's doing it, right? So let's flip-flop these. So if you're saying the bottom of this mux is 0, then this will be 1, right? And if you're saying the bottom of this mux is 0, this would be a 0. All right, so yeah, these numbers are, convention, right? Do I define the bottom of the mux as 0? Do I define the top of the mux as 0? But just, I'm sure if you show, I'm selecting this bottom line right here, this top line right here, you'll be okay. So, any questions about this particular control block or control diagram? So the control numbers depend on the function. Yes, they're going to depend on the opcode, right? Because what's going in right here, right? So this is bits 31 through 36, and I said the first 6 bits are the opcode, and that goes into this controller right here, which is a decoder, and it's going to set all these control lines. So the controls are going to be set depending on the opcode. So every opcode is going to do a different thing to this controller. And like I said, these control lines, I maybe wouldn't recommend memorizing, but you can definitely figure them out by working through it, right? Like at this mux, right? I want to figure out what this control line, if it's a 1 or a 0. And for convention, you guys said she usually has the diagrams as the bottom is 0 on the mux. So, right, in our ALU, this is an add immediate instruction, and I want to add the immediate value to whatever RT is, right? So if I have a choice between RT and the immediate value, right, I should pick the immediate value. So that's how you would figure that out, right? And if the bottom of the mux is 0, this control line would also be 0, right? Or at this mux, right, I have, what is this mux going to do? Am I going to select, should I select, what would traditionally be the RD value, or should I select RT as the destination? Well, in this particular example, we said RT was $T3, right? We want to write to $T3, so it makes sense to select this top mux line as what's going into RD. So then you would know this should be, right, if this is 0 and this is 1, you would select 1 as this mux line. Yeah, so I'm not entirely sure what Zybooks says. I've never taken, an exam in your particular version of this course. I was here when Dr. Dodge was still teaching, so um, I'm just here to maybe show you guys some insight, but I'm not sure, what exactly needs to be done on this final exam. So do we have any more questions about this computer architecture question? If not, I'm going to go more into some digital logic type questions and work from there. What are the different ALU operations? Can you write out all the control values? Okay, so like in a list almost. All right, let's see if I can write out these control values. So for this particular instruction, right, I said that, like, let's just go by down, right? So this is RF, right, ADDR, S, right, which is this control line right here. I said I'm taking the top of the mux, right, by looking at the diagram and seeing where the data is going to flow. So that should equal 1, right? This PCS, right? So this PCS is going to control this logic right here, right? And what does this logic go to? It's going to this mux right here, right? And it's going to select whether I should take, so what is this calculating right here? This is, so let's talk a little bit about branching. So yeah, pass fail has been implemented. This is just my suggestion, not official or anything. If you know you're going to make an A in the class, it's to your advantage to declare the class as, or to not do anything, right? Just take the A in that class. It'll help your GPA. But if you're going to get a grade in the class that might lower your GPA, right? If your GPA is a B plus average and you're going to make a B minus in the class, it may be to your advantage to take it credit, no credit. But if you know you're going to make an A in a class, I would not opt for credit, no credit. I would just take the letter grade. Anyway, let's go back to here. I was talking about control signals. So right now I'm talking about this, this PCS branch. What should I do for this, right? Well, let's think about what's going on here. So let's talk about branching. So in instructions, right, typically you go to the next instruction, right? You go to the program counter +4, because that's in an assembly program. If you're going down instructions, that's what the next instruction is going to be at, because each instruction is 32 bits, which is 4 bytes. So typically, if we're doing some math instruction, if we're not doing a branch, right, you would just go to the next instruction. And we see right here, this takes the PC counter value and adds 4 to it. So this is like the next instruction, right? This is like, the next instruction that's being calculated right here. And we see that goes all the way here, right? And it goes into this mux, right? So naturally, we would want to select the top of this mux, right? For this particular instruction, are we doing any kind of branch? No, we're not. I just want to go to the next instruction, which is calculated right here, right? So I want to take this one. So I want, if we're doing our convention, if we define this as 0 and this is 1, I want to take a 1, right? so I know you guys said I think the mux convention really is this is 0 and this is 1, right? Because typically we would want to take this branch, right? This is branch with a question mark, right? We're not branching in this instruction. So, right, we would want to put a 0 here. Because when we have a 0 here, that's going to send a 0 to this AND gate, right? And whenever you have a 0 for an AND gate, it doesn't matter what the other outputs, what the other input is. It doesn't matter what happens to it. It's always going to be a 0, right? And so we would send 0 out here on this gate. And that would make sense if this top one, you know, this top value, if 0 on the mux corresponded with this one, right? If we define the mux here as, you know, note this, right? If we define the mux values here as like the top of the mux is equal to 0 and the bottom of the mux is equal to 1. I think that's generally how it's denoted. Right, okay, so Max is saying this mux is the only one that breaks the convention. Okay, right. Yeah, so this is a convention. So this mux should be coded as this, right? Because we're saying we don't need a branch, which will force this gate to 0, and we want to pick this top one, right? Because what this will do if we force this one, if we take this branch, that's going to get fed back in here, right? And it's going to go back to the program counter, which is going to set the next instruction, right? So she has it both ways. Yeah, so I guess maybe if you do this, maybe just make it to where if you have the convention either or, it would work, or maybe state what convention you're using. I generally do it, you know, the top is 0, the bottom is 1, but so right, with this diagram, you can kind of figure out what these instructions need to be, right? So, all right, this PCS is equal to 0, right? Because I'm not branching. Let's look at this one, this DM read enable. So that one's going over here, and I already said this one's equal to 0, right? Because I'm not reading from main memory. This one, this like RF write data S. That one's going over to this mux, right? It all depends on the convention you're going to use, right? So if, you know, you're going to use the convention that the mux value at the bottom, like if this is 0, right, you'd put a 0, or you'd put the other way around if you're flip-flopping it. So I'm just going to go, you know, back to the convention we originally had. Like, let's say the top of the mux is equal to 1 and the bottom of the mux is equal to 0, right? I'm selecting the bottom mux pass, so let's put that as a 0, right? All right, let's go to this ALU op. So what type of ALU op are we doing here? We are doing a add, right? And I'm not sure if we, right here. So right, this function corresponds to what this is right here. This ALU op is the same thing as this function. Right, well, let's double check that actually. Okay, so yeah, so we have. Okay, so the convention is written on the exam, so just use the convention they give you. This ALU op is right. It's going to be something that says we're going to add. I'm not sure what value that's encoded as, but just know that's, you know, kind of what this operation is doing with this ALU. DM write enable. That's equal to 0, right? Because I'm not writing to main memory. Okay, so let's look at this add to S signal here. So this signal controls this mux right here, right? And what is this mux selecting from? It's either going to select the my picture. It's this you know, add to S right here. It's either going to select this bottom or top one. Like I said, we're doing this immediate value, so we want to pull this immediate value, that sign extended down here, into the fray, right? So if the bottom is equal to 0 on this mux, that value is going to be a 0. And then this RF write enable, this is a write back instruction, right? I'm writing, you know, my calculation from the ALU back into a register, so that's going to be equal to 1. Yeah, so does that answer your question about how to pick, you know, what the values of your control lines are going to be? So right, if you can kind of trace out, you know, what data path you want everything to take, then you can kind of see, you know, this mux needs to take this path, and this mux needs to take this path, and this mux needs to take this path, and then figure out, you know, what the value of the mux should be. Any more computer architecture questions? What is a function for an ALU op? So let me go back to this, right? So the function code is used for what's called an R-type instruction, right? And whenever we have a function code, it's in the bottom 6 bits, right? It's bits 5 through 0. And bits 5 through 0 are going to be, you can see right here, this function code is going to be fed into this ALU control, and that's going to determine, you know, what this ALU does, whether it does a read, an add or subtraction. But this line only really matters when we're doing a R-type instruction. This is a immediate type instruction, so this ALU op is going to control, you know, exactly what this ALU does. This part won't have any influence on what this ALU control actually does with this ALU. And yeah, so the sub is the exact same way. Like if I had replaced this instruction with sub I, it'd be the exact same as far as control would be in this. Now you would have a different instruction, right? The only thing that would change about this is instead of having opcode, you know, hex 8, you would have whatever the opcode for a sub I is. It's not listed on this particular chart, but that's what would happen there if we had, you know, sub I instead of an add I. All right. Gonna wait one more on any more computer architecture questions, and then I may move on to some Boolean algebra type equations. All right, no more questions on that. I'm gonna switch gears here and talk a little bit about Boolean algebra, and I'm gonna do it mainly through some example questions here. So let's pull up an example problem here. And so we have a simple example here. So let's say we have some function, right, of a, b, c is equal to a. So let's use Boolean algebra to express this function as a canonical SOP, right? Sum of products. And so sum of products, just quick review on that. Sum of products is when you have an equation where each term has it's ANDed together and the terms are separated by an OR. So this would be, right, like an SOP equation. And then product of sums is going to be kind of the inverse of that. We're going to have terms that are, have an OR on the outside, on the inside, and then they're going to be separated by ANDs. So something like this. So we want to create a canonical sum of products. And what that means is we want to expand this equation as much as possible. Like for every term of the equation, I want to see A, B, and C for every single term. So how can we go about doing the expansion of this? Well, what I can do is I can use some laws of Boolean algebra here. So right here, I have an implied 1, right? Because anything ANDed with 1, it's just itself. It's a pretty common property. So what we can do is leverage that property, right? Because we can leverage another property that says a variable ORed with its inverse, right, is always equal to 1. So using that, that should be an A. Right, anything ORed with its inverse is always equal to 1. So we can kind of leverage that property here. So A, right, I want B and C and A to show up in every single term. So what I can do is write down this property here, right? And multiply it or AND it with this right here. And so these are both, 1, right? So I haven't done anything to this equation. It's still just A. I've just kind of written it in a different way here, right? And what I can do is I can distribute all these terms to each other, right? So if I do this distribution first, I have A, B plus A, B naught, right? And then I have C plus C naught right here. Then I can distribute this again, right? It can be ABC plus AB C naught plus A B naught C plus A B naught C naught, right? And so this is going to be our, our canonical SOP equation right here. Every single term in my equation has, all the variables in it, as A, B, and C, A, B, and C, A, B, and C, all that. Does that make sense to everyone? So I'll wait 1 minute to see if anyone has any questions about that. All right, so next I'm gonna go into like the compact forms that we have. So we can kind of, when we have these equations, we can kind of do like a shorthand form of things to where we can write them as just the terms. Right, if we have A, B, and C, the number of different possibilities we have is 2 to the 3, right? So there are 8 different possibilities, right? And it's like a truth table, right? Where we have 1, 2, 3, 4, 5, 6, 7, 8. And then we have what the function output's going to be, like this would be 1, 0, so on and so forth. It's like a truth table. So what this, when we say, let's convert this to the compact SOP, what we want to do is we want to write the terms that make the equation, that make the function true, right? So what we can do is, once we have this canonical SOP, we can find out, what terms we have, right? So this term is 1, 1, run, right? Which is equal to 7, right? And this term is 1, 1, 0 right here. So that's equal to 6. We have the term 1, 0, 1. And that's equal to 5. And then we have a term right here, which is 1, 0, 0, which is 4. So we can say, instead that f is equal to the sum of min terms 4, 5, 6, 7. And that's a more compact way of, saying the same Boolean equation. That means exactly the same thing. Let me pull up some more notes I have here, and then we'll kind of continue with this. Right, okay, so we have this. Let's kind of reorganize things here. So this was our canonical statement, right? A, B, C naught plus A, B naught, C plus. And we had our compact SOP, right? So the compact POS is like the opposite, right? It's all the terms that make the equation go to zero. And so it should be the complete opposite of the SOP, right? So it should be all the terms that are not in the SOP. So you can write this as the sum of the product of max terms, and those are equal to 0, 1, 2, 3. It's just, you know, everything that's not in the compact SOP. Right, so that's pretty simple. So let's finally let's do a conversion from SOP to POS. And what we're going to use to do this is we're going to use De Morgan's law. To do this conversion from SOP to POS. And so what De Morgan's law says is, right, if I have something like this, what I can do is, if I want to write equivalent statement, I can combine the lines on these terms and change the sign in between them. Combine the line and change the sign. So we have something like this. These are equivalent statements. And then I could do the opposite, right? If I start out with this, I can change the sign in the middle of these two and distribute this line. Break the line and change the sign. It works both ways. So we want to try to convert this POS equation we have, this SOP equation we have up here to POS. And how we can do that is we can take the entire equation, C plus A, B, C naught, and we can double invert it. So we're going to put two invert lines on top of it, right? So we've done that step. Just make sure. So what we want to do, right, if we want a POS equation, or let's see, this particular problem said to take right, F naught, right, which is going to equal, you know, A, B, C plus A, B naught, C naught plus right. So write F naught in SOP form. Use De Morgan's law to convert F naught to F expressed in POS form. So we've done this step, right? We just put a big invert line over all this. And what we can do is we can start breaking this apart using De Morgan's law. So what I'm going to do first is I'm going to write in a POS statement. What I want to do is I want to break these plus signs apart. And so how I'm going to do that is I'm going to apply De Morgan's law. I want to change these to ands. So what's going to happen is I'm going to break the line and change the sign. So this ABC is going to become inverted. And then right here, we're going to have A, B, C naught. It's all inverted. And then A, B naught, C, A, B. So of these, I just inverted the tops. And now what I want to do on the insides is I want to convert those to pluses to get it into SOP format. So how am I going to do that is I'm going to apply De Morgan's law again here. And so I can break these apart. kind of expand this out. Right, and on this term, since, you know, if I break apart this bar right here, it's going to do like a double invert. So that's just going to be C instead of C naught. And same thing with this B right here. And then this is ANDed, right? So we end up with something like this. As our POS equation. All right, any questions about that? So typically when you have to go from a POS to SOP or vice versa, you're going to use De Morgan's law to change the signs and manipulate the equation. So right, it's important to understand, you know, how De Morgan's law works and all that good stuff. So let's maybe do another type of logic question. Let's pull up another one here. So I'm assuming you guys might need to do something like you have an equation and you need to convert all the terms in your equation to Nand or NOR gates. So let's talk a little bit about that. So Nands and NORs are interesting because they're logic complete, which means that you can form any equation using only Nands and NORs. And so, right, let's write some NAND gate equivalences. So let's say you want to make an inverter. How can you do that with NAND gates? All you need to do is take a NAND gate and tie the inputs into itself, right? This is the same thing as an inverter. If you want to make an AND gate, right, a NAND is just an inverted AND, right? So if you take the regular AND gate and add our newly created inverter like this, you get the same function as an AND. Right, we need one more. We need to figure out how to make an OR gate. And what we can do is we can kind of, again, leverage De Morgan's law here. So, right, this is the Boolean equation. This is the Boolean equation for an AND gate, like this. And if we, let's say we took an AND gate, right, and inverted both its inputs. This. What's going to happen is when we do this, right, this is the same as writing this. Right, it's like a NAND, but the inputs are inverted. If I apply De Morgan's law, I can combine the line and change the sign here. That's a double negate, right? So that's just A plus B. So that's why this OR gate works like this. So these are the things you need in order to write any type of circuit using NAND logic. And the same thing is pretty true with the NORs also, right? The NOR, the inverter is exactly the same. Only we have a NOR gate, right? This is the inverter. And the ANDs and the ORs are switched. So to make an OR gate, right, it's just NOR gate with its output inverted. And to make an AND gate, you invert the inputs. So that's how we can convert anything to AND or NOR logic. So let's do an example. So let's say we have a function A, B, C, D, and it's B naught D plus A D naught plus A naught B naught plus C D naught. And we want to use only Nands, right? How should we do this? So I see someone's asking about how to, maybe if you start out with a POS equation, how do you do that? I can get to that after I do this example. So let's convert this to NAND. So what we can do is we can do this graphically, right? So we have an AND gate right here, right? And we know I can make an AND gate using NANDs by taking just regular NAND gate and putting our NAND inverter in front of it. So this is like an AND, right? And what's going into is D, and we have B inverted, right? So just let's build the NAND inverter, put B into it. All right, we've got this term done. Let's do the next term. It's the same type thing. It's an AND gate, so we take our NAND, invert the output, and we have A going into it, and we have an inverted D. So let's make our NAND gate inverter and put D here, right? So we need two more terms. Right, we need inverted A and B. So we're gonna have our NAND gate inverter here. We're gonna have two here, and we're gonna feed both A and B into them. Right, this is A, this is B. And then we're gonna have our last round here. We're gonna have C and D, right? All right, so this is what we have. We have all these individual terms. Now we need to OR them together. So how do we do that? Well, we can create our OR gate using the names. So let's go ahead and do that. Right, so how we do that, right, is we take the NAND gate, right, we need one stage and then like a last stage, right? So these will OR, this part will OR these two together, this part will OR these two together, and then this will finally OR the last part together. So what we do is we want to invert the inputs, right? And then we want to connect these together like this, right? But what we can see here, right, is look at this. I'm doing an invert and I'm doing an invert right after that. That's the equivalent of not doing anything at all. So how we can simplify the circuit is we can get rid of these inverters right here and just connect it directly to this gate. And the same thing is going to be true here. Remember, we're making an OR gate, so we will not this inverter right here, this inverter right here, and we can see we have, double inverters right here, so we can get rid of those also, save gates. So now we have this, and we want to make one more OR gate to invert the last stage, or to OR the last stage, like this. And this is our completed circuit. So that's how you create a circuit with only NAND gates. NOR gates are the same process, only you're going to use the NOR gate equivalences instead of the NAND gate equivalences. So I won't do that particular example unless someone asks for it. So do we need any more clarification on POS? I can kind of show you how you would calculate your terms for the POS. So let me just write some basic POS equation. I'm just going to make up something here. Right, is equal to plus B naught plus C naught plus A naught plus B C naught. Okay, so we want to write like the product of max terms, right? So how do we do that? Well, what does this mean? It means what are the terms that make the equation go to 0? So let's look at this POS equation, right? What has to happen for this equation to go to 0? Well, as long as one of these ands are equal to 0, it doesn't matter if it's that one, it doesn't matter if it's that one. The entire equation is going to equal to 0, because anything anded with the 0 is just a 0. So when we create our terms here, we want to think about what has to happen for this, whatever's inside the parentheses equals 0. So let's look at this, right? If A is equal to 1, inverse of 1 is 0, right? And then you would get 0, and that wouldn't do anything. With these OR terms, right, we can remember that anything ORed with a 1 is always going to equal to 1. So what we want to do is we want the result of all these OR and inverts to be equal to 0. So remember how in SOP, if this was A naught, we would put like a 0 right here. This is like opposite. So if we have an A naught, or a variable knotted, we actually put a 1. So this will look like this: 1, 1, 1. This is 1, 0, 1. You kind of do the opposite, and that's what gives people a lot of trouble. So right, we can go to write these terms now. So right, this is the equivalent to 7, right? This is the equivalent to 5. Right, and as Joshua said, right, if I had this term right here, A plus B plus C, right? Normally in an SOP we'd write 1, 1, 1, but for POS it's the opposite, right? This is 0, 0, 0. So for this particular equation, right, if you had this, you'd write this, right? All right, so he's saying when we turn the SOP to POS, we had so the last example wasn't like a true SOP to POS, because the question I had here said to this particular example question said write F naught in SOP form used De Morgan's law, convert F naught into some equation expressed into a POS, right? So So someone's asking, what if you wanted to find the product of max terms instead, right? So we can go back to that example real quick. Right, so this f was equal to a, b, c was just equal to a. And we just know, right, this canonical was equal to, or we know this product of max terms, right? Right, if the equation is equal to a, then right, we have a truth table that goes 1, 2, 3, 4, 5, 6, 7, right? And for these, a is equal to, 0, and for these, a is equal to 1, right? So we can say, for this one, we're going to have these terms, 0, 1, 2, 3, right? So that's where the equation's equal to 0, right? And so maybe we want to write this as like a canonical POS equation. So what we do is we would have, right, 4 ands. And then for this one, right, it'd be like a plus b plus c. This one would be a plus b plus c naught, right? This one would be a plus b naught plus c. And this one would be a plus b plus c. For now. Let's be this right. So that's kind of another way of trying to find out like how to do like a POS change, right? If you can figure out what the min terms are, right? In this case, it was 4, 5, 6, 7. The max terms are just going to be, what's not included here, right? And then you can convert this equation, you can convert this to POS like this in this way. So yeah, you can kind of do it. There's several ways to go about it. This way might be, a little bit less risky. You're not doing a bunch of Boolean algebra trying to get to the result. But I just kind of wanted to showcase De Morgan's law on that last one. So right. Okay, so we kind of covered the differences between POS, SOP. Remember, POS is weird and right, it's kind of like you're wanting to do the opposite, right? Because in like a normal POS, if you had like a 0 term, you would be thinking a plus b plus c naught, right? But POS is the opposite. It's, a plus b plus c if you want to represent like the 0 max term. And I've covered the Nand gate equivalences and the NOR gate equivalences and how you will find them. So let me just look back through the chat and see what else we want to go through. Someone says how to count up the transistors. So let me see if I have an example problem for that. I'm assuming you're given maybe like a circuit and you want to count how many transistors each one has. Pretty straightforward. So let's see if I can find something like that. Just give me a minute here and look through what problems I have. So I'm assuming on the exam she might give you like some kind of K-map. I think we went over K-maps earlier in the year, but I can kind of do one example problem. This might be one of the last ones I do tonight, maybe showcasing kind of a gate sharing operation. So let's look at this. Let me share my screen here. So we have this problem right here. So use K-maps to minimize the following output function using SOP. And we see we have 3 4-variable equations, and it's given to us as the sum of midterms. So we want to use a K-map to minimize these outputs. And what we want to do is then estimate the number of transistors required to implement the system using no sharing and doing transistor sharing also. So let's kind of look into how we're going to do that. So we have, let's just go through how to do a K-map real quick. We have one equation here that's this G function. This is equal to sum of midterms 0, 1, 6, 7, 8, 9, 14, right? So how should we go about doing this? Well, first what we want to do is we want to come up with, our K-map. So if we have a 4-variable K-map, right, we're going to form a grid like this. So let this be like AB, and this is CD right here. I'm going to number them right, 0, 0, 0, 1, 1, 1, 0. And right, the K-maps kind of use the gray coding on the top, so the numbers are a little weird, right? This is 0, this is 1, this is 3, this is 2, this is 4, 5, 7, 6. Go down here. This one right here is 8, 9, 11, 10. This one's 12, 13, 15, 14. So let's do this K-map here. So in a K-map, the midterms are going to be what you write in as ones on this K-map. So G, we had midterm 0, which is right here. So I'm going to put a 1 right there. I have midterm 1, which is right here. I have midterm 6, which is right here. 7, which is right here. 8 is right here. 9, 14. This is what my K-map is going to look like. And I want to form the best equation I can. So I want to form prime implicants, which are groupings of power of 2. So I can group 2 adjacent ones together. If I had something like this, right, I could group all 4 of these together since they're all adjacent and form a power of 2. Unfortunately, I don't have one right here. I have a 0 right here, so I can't really do that. So let's kind of see what the best ones are. And what's a little tricky about these K-maps are the adjacency will go across the edges right here like this, right? So look at this right here. They can kind of wrap around like this. So I can already tell you there's a prime implicant right here that I'm going to circle that goes from here to right here. Because the top of this is it's connected to the bottom of this right here. So I can form a prime implicant like that. Right, so that'll give me a nice group of 4. So what I'm trying to do is I'm trying to form the biggest groups possible. And for vice versa, just for kicks, right? If I had ones right here, I could do a wraparound that went like this, right? And like this, that would form a group of 4. So just be careful. Sometimes you can form bigger prime implicants if you can kind of wrap around the edges here. So this, unfortunately, I don't think there's any way for me to form a group of 4. So we're gonna break this up into 2 groups like this. All right, so once I have all these ones in a circle in a prime implicant, I can then go to writing the simplified equation. So how do I write the equations? Well, I'm gonna look at this grouping, right? So I have this, and this. This is all in the same prime implicant. And I want to see how these numbers change on top, right? I can see that for C and D, right, it goes from 0, 0 to 0, 1. And I want to write down how I'm going to form my equation, right? So this is going to be the new G simplified, right? How I'm going to write this down is I'm going to look at what variables change and what variables don't change, right? So here I can see that, let's look at this. We go from 0 to 0 to 0, 1. Well, C stays the same, right? But D's the one that's changing here in this particular case. So I'm going to take, whatever variable's changing, and I'm going to discard that one. And I'm just going to write down what variable is staying the same, which is C in this case, right? And C is equal to 0, it goes from 0 to 0. So that term is going to be C naught, right? And then I'm then going to look in this dimension, the other dimension right here. I'm going to look between this 0, 0 and this 0, 1, because that's where the ones are. So I'm saying that A is changing from 0 to 1 and B is staying the same. It's staying the same, right? So that's going to be, right, B naught. So that's my equation for that prime implicant. So, and we're going to do this for everyone. So, right, this is SOP right here. Since we're circling the midterms, whenever you're working with midterms, it's going to be SOP. Let's look at this prime implicant right here. Let's look in the AB direction right here. So the only, kind of row where this stays, or where the ones are, is this row right here. And we see A and B don't change. They're 0 and 1, but there's no changing because this doesn't occupy more space in the Y direction. So we're going to write down these, right, for this term. So we're going to have A naught, B, and then we need to do this direction, right? It goes from 1, 1 to 1, 0. And C is what's not changing, right? C stays from 1 to 1 while D is changing. So we're going to write down C here. That's what we get for that term. Let's go down to this grouping right here. Yeah, so you admit the changing variables. So if a variable is changing, between in your prime implicant, you're not going to include it, right? That's how the K-map simplifies terms. It's dropping those. Essentially what it's doing, right, is whenever you have a variable that changes right here, like you see that the D goes from a 0 to a 1 here, it's essentially what it's doing in Boolean algebra is like this, right? And so we know from a property that equals 1, and 1s are redundant, right? We don't need to do that. So that's how we can drop that term. And a K-map is a visual way of saying that. So, right, I'm going to do this last one. We see right here in this axis, the AB. A is changing, and B stays the same, and B is equal to 1. So we're going to write down B. Let's look at this axis right here. We can see that C and D stay the same. They don't change, right? So C is 1 and D is 0. So this is our simplified G equation. All right. Do we want to do one more K-map, or do you guys kind of want to see sharing? So Erase this and let you guys respond. I can kind of go into how we would share. Yeah. K-maps should kind of be a review, right? I think I went over them a little bit later. So in this problem, there was 2 other K-maps that I did. I'm just going to give you the results of those. So this is all the simplified equations. We have 3 equations here, right? So F was this, and B, C, D naught plus. So if we do 2 more K-maps, we get these equations. And how the sharing works is I want to look at what things these equations have in common. So just kind of visually inspecting. Oh, look at this, like right here. We have this, and then we have this one right here. These are shared, right? So if we were to do a real circuit, right, if we could write all these as separate, but we see that we're calculating the exact same thing twice in both equations. So if we went out to make a physical implementation of the circuit, we could just write one of these gates down at step 2, right? Because they both have the same inputs, right? It's the same gate. So that's how the sharing works. So we want to search around and find things that we can share. So look at this term, right? This A naught BC. It appears in this equation also, and in this equation, which is convenient, right? Let's kind of search around some more. Oh, look at this, right? This appears in the equations too. Right, so these are the things that are being shared. Right, these 2 are the same. These are all the same. Right, these 2 are the same. These 3 are shared, and these 3 are shared, right? So are you guys kind of doing the approximation that 1 gate is equal to about 2 transistors, correct? I got that right. So, right, if we were to, so let's say like how many transistors we got right here. So how many, so like this is no sharing, right? So let's see. We can go over calculating transistors. So I'm not sure how Dr. Kogan's doing it now. When I was taking the class, each gate kind of translated into 2 transistors. I'm not sure what she is saying nowadays, but I'm not sure if anyone has insights about that. But typically, how to calculate transistors is you want to count 2 times the number of inputs plus 2. Okay, so that's kind of the formula we use, right? So right, we would count all the inverters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have like 15 inverters. And then 2 times the number of inputs plus 2. we don't count all the inverters. Yeah, that's what I had in my example. So I kind of have the work here already. So let's go back to my example I had here. So I think what I did here is, you know, kind of ignored the inverters here and kind of counted how many gates I have in each function. So here I have 1, 2, 3 OR gates, 5, 6, 7, 8, 9. Right, so I had, no, these are different counts. So this equation, I had 1, 2 gates here, 3, 4, 5. I had this many gates, this many gates, this many gates, and I think when I was doing this, I were able to double the transistors. One inverter per occurrence of the literal in each equation. Right, that makes sense. So it seems like we've kind of changed how we're going to calculate this. So we can kind of do this together, right? So let's take this this G equation. So we have, you know, B not occurring, we have C not occurring, and we have A occurring. A not occurring, and we have D not occurring, right? So we have 4 inverters. Because those literals appear every single time in this G equation, right? And we said that the equation is going to be 2 plus the inputs right, so that's equal to 8 plus 2. And so right at the, so we have 1, 2 input AND gate. So that would be 6, right? Plus this one, I have 3 inputs, so this would be 6 plus 2, which is 8. Then I have this one, which is 2 times 3, which is 6, plus 2, which is 8. And then I have all these OR gates. So I have a 3 input OR gate, which is equal to 8. So when we add all those together, I get 30, right? Plus the 8, so 38. Does that look correct? So if this is the correct equation, you go through all of these and count up how many you have. And so, but I think what's been consistent throughout the years is the sharing, right? So when you were to calculate all these transistors, right, you calculate G first, and then any occurrence of this literal or this literal that occurs in F, we don't have to account for anymore since it's already accounted for in G, right? So, you know, I'd count all the transistors in these gates plus the ORs, and then when I go down here, I'd count the transistors in this gate plus the OR plus this gate plus the OR. But I wouldn't have to do this one because I've already accounted for it in this term right here. And then I'd count how many this gate contributes and then all the ORs, right? And for H, I wouldn't have to count this one, or this one because I've already accounted them beforehand, right? And then I'd add up all our transistors. So typically sharing will reduce the amount of transistors you'll have. Yeah, so I think, like you guys said, I don't really know the exact equation for this, but I can tell you, right, about the sharing process. And, you know, I would double check on what exactly this equation is. But, right, we kind of went over a K-map. You guys possibly maybe want to see K-map using BOS terms. I know sometimes some people like to see that way. So instead of using the min terms, we use the max terms instead to calculate what the equation is going to be. So let's do POS. Kind of K-map looking thing. So remember we had G, and G is 4, right? 4 input. It was 0, 1, 2, 3, 6, 7, 9, 10, 13. Well, we want to do product of max terms, right? So it's everything that's not in here. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So this is what we want to use. And so we're going to draw our K-map again. We're going to do the same process, only a little bit different. We're going to be working with the zeros this time instead of the ones. So, right, just number this up for you. 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. And so for these terms, instead of like, right, if we saw there was a 4, we put a 0 there, 1, we would put the 0 here instead. So let's look at 4. Right, the 4 is right here. I'm going to put a 0 instead of 1, right? Because this is a product of max terms. I have a 5 right here. I'm going to put 0 there. 8. Right, go ahead and these zeros in. I think it might be an equation here. Okay. So, right, I had 8 is this one, 11 is this one, 12 is this one, 14 this one, and 15 is this one. So I have my max terms sorted out, and I'm going to do the exact same thing I did for the minterms. I want to create the biggest prime implicants. So I'm going to kind of evaluate, what I can circle. I'm trying to maybe get a group of 4, but I don't think there's any way of getting a group of 4 with this one. So just going to circle what I can, right? So I can do this one and this one and this one and this one, right? So, right, I've got my prime implicants. Now I can convert these to an equation. So, right, we're gonna kind of do the same process here, but it's kind of backwards, right, because of how the POS works. So let's start creating terms here, right? I'm gonna end up with 4 equations since I have 4 prime implicants. Might run out of room here. Change these up. All right, so let's try to do this. So we have on this one, we have A and B, and they're not changing, right? So we're gonna have and up here, we're gonna see that C is also not changing. So we're gonna have something like this, right? And remember, it's the opposite. So A is 0 here, so we're gonna write it like that. B is a 1 right here, so we're gonna write it like this. And C is a 0 right here, so we're gonna write it like this. So this is gonna be our first term right now. And so Joshua was saying that's a good point. So what would it matter if the prime implicants are different but still cover the same squares? No. There's different right answers, right? Because right, I'm trying to cover the most implicants, or the most terms with the least amount of implicants, but there's multiple ways to do it. Like, instead of doing this crisscross right here that I did, you could do this, right? You could wrap around like this and do this, and you would get different turns but the same level of complexity. Like, it would still be simplified, but there may be 1 or 2 most simplified ones that are the same level of complexity. So as long as you cover the most terms with the least number of implicants, you're good. And there may be 1 or 2 variations of that, right? There's 1 or 2 different ways you could cover it to get the same amount of prime implicants, right? So this is just the particular way I did it, but that's a good observation. All right, so let's do this one. So let's look at this column. A is staying the same, A is 1, so it's like we do the opposite, A not. Right here, we can see C and D are both 0, so plus C plus D, right? And, instead of ands, we have ors. Let's do this one right here. We can see that A stays the same and B doesn't, and a is equal to 1, so this is our a naught. Right here, C and D are staying the same, and there's both 1s, so we're going to do plus C naught plus D naught, right? It's that opposite thing. If it's a 1, it's actually, you put the invert over it. All right, and we have this last one here, and this axis, you have A naught plus B naught. And this one, C staying the same. All right, so now we have our POS equation. So that's how you would do it, right? If you wanted to do it with the max terms. And all these that I didn't fill out, these have an applied 1 right here, right? They're 1s. And you could do, if we wanted to do it, the normal way, the way SOP, you could circle this primitive. But when you're doing the POS, you're going to work with the 0s, and when you're doing the SOP, you're going to work with the 1s. All right, I think we're kind of running out of time here. I'm not sure if maybe someone has a suggestion of one more thing to cover. I know someone wanted maybe the interrupts and the poles talked about. So I'm not sure if I can give that much information about what exactly is going to be on the test regarding interrupts and poles. But how poles work is it's CPU controlled, right? So typically how a pole works, like let's say we're talking about something in the C language, right? We have like a while loop. And then we have like some function that's like, I don't know, like, right, like a digital read, right, that we have in like Arduino, right, and then we have some variable, right, and we're saying that's equal to like a C or something. This is what we call a pole periodically, right? So the CPU is gonna like run this loop, and periodically the CPU is gonna like sample, hey, what's this, pin value, right? It's gonna periodically check. And what a pole does is like it's like a checking on a timer, right? So I'm always like, going back to this and checking it manually. That's how a pole works. And an interrupt, right? An interrupt isn't like controlled by the CPU. Whenever an interrupt happens, it's there's some circuitry inside the microcontroller, what have you, that triggers it whenever it changes. So let me see if I can get to your guys' slides, maybe, and explain it more with the slides that you guys have for the class. Right, so we have the class slides, right? So the pole, right, we have program IO, which is what I was saying, like the CPU is constantly checking like the status of like a pin or some analog reading, and it's doing it like almost like a while loop. I like to think of this like in a while loop. It's constantly going back and checking, and it's typically written in software. It's serviced by the CPU, right? Because the CPU's checking it itself. And the processor is wasting cycles, right? Because I keep on checking this thing periodically, even though like the value like doesn't change over time. While with an interrupt driven IO, right, the device only sends a signal when something changes, right? Something has to change. It's a hardware mechanism. It detects whether something flips from a 0 to a 1 or a 1 0, right? It doesn't do anything if the state stays the same. While in the poll, right, like you're constantly checking. So even if the value doesn't change, right, your CPU is still firing in this loop. Right, the interrupt can take place at any time. It's like an asynchronous thing. Right, as soon as the value changes, this interrupt's going to be serviced. And well, when you have a polled IO, right, it's constantly checking, and if the value changes in between when the CPU kind of polls it, it checks the value. It won't know until like the CPU eventually does the check again. So, do you have any particular questions about the IOs and things? Maybe between a poll and a interrupt. I could probably give you more specific information if you kind of ask a targeted question. And also, while we're at it, we're at 9 o'clock here, so I'm gonna try to wrap things up. And if anyone has any more questions they'd like to go over, is I squared C a example of programmed I/O? So what does it mean if something's vectored? So in microcontrollers, when we're talking about vectored interrupts, is so polls are never vector interrupted, but when I have like a vector interrupt, right? I have like a C program, right? I have like a C program, and maybe I have some processing loop, right? And it doesn't matter what's in this loop, it's just doing something. Like I have like normal code right here. And if I have a vector interrupt, right, let's say, I'm doing some code right here in this part of the program. And let's say, my interrupt is set up to, I want to interrupt whenever a pin on my microcontroller goes high. So while that pin's, not changing, the state's the same, I do this code. But as soon as like the pin goes high, it like triggers an interrupt. What happens in the microcontroller is there's a table called a vector table, right? And it lists different interrupts. Like might have different numbered interrupts, and here it has like a program counter value. And what that program counter value points to is some other piece of code right here. So this is some loop we have in our code, and right now we have like some void function that's like interrupt handler, right? And what this does is whenever we have an interrupt that's triggered, it looks up, hey, interrupt 1, happened. And what I do, right, is I look at what's the value of this program counter, and this program counter will point to like a certain interrupt handler, right? And so whatever the CPU is doing right here, it's going to jump over to this and then run whatever code's here, and then whenever that code's done, it's going to jump back here. So that's what a vectored interrupt does. It, whenever something happens, like the state changes and the hardware notifies the CPU will go to this table, this vector table, and look up what location is my interrupt handler, and it'll run that code, and it interrupts the processor. Whatever the processor is doing, it stops it, saves its state, runs this interrupt function, and then goes back. And so, right. And, polls just constantly check it over a certain interval. They don't have like this vectoring thing, right? So any more questions anyone has? So I'll stay here for about 5 more minutes to see if there's any more questions. I hope this was of some use to you guys. There's a few stumbles, and part of that's because I haven't, I guess I'm getting too old now, and the curriculum has changed a lot since when I've taken this class. So a lot of times I'm not able to give you guys specific examples on what might be on the exam, but I can, I'm more good at maybe trying to explain some of the topics, or maybe if you have a certain problem, the methodology of how to do that. So I hope this was of some use to you guys. The COVID situation and online learning makes it a little bit harder to run these, but I think I'm getting slightly better. I think this whiteboard here I had makes it a little bit better to read things than like the document camera I had before. So I hope you guys do well in your exam. If you have any more questions, you can probably post them in the IEEE tutoring channel. I know that some guys are watching that later at night. So thank you guys for attending, and I hope you guys do well on the test.